So it is just about 1 o'clock, and I'm excited to be here with you for our 1 o'clock class from the Fairbanks Museum and Planetarium. In a moment, I'll turn things over to our extremely talented AmeriCorps science educator, Michael Simoniello. And I just first wanted to introduce you all to the Zoom platform that you're on right now, as well as the YouTube platform that some of you may be taking part in today's session through as well. For those of you on Zoom, you're lucky you have the highest amount of interactivity with Michael and myself today. Some of you have already discovered the chat function. So if you mouse your cursor down to the bottom of your screen on Zoom, you'll see that there's a little chat box. And as you can tell, there's a bunch of folks already on there chatting away. That's one place I'll be checking during today's session for questions while Michael is teaching. The other place you might also try posing a question is if you click on that Q&A box. So that Q&A box is a wonderful place to put a question in. You can even ask one anonymously. If I'm able to answer it, I will do so in writing form. If Michael answers it live in the session, I should say, in today's class, then you'll be able to actually hear him answer it, and I'll just mark it as being answered live in the session. And then finally, the other way that you can join us, and this is only for those of you on Zoom, is if you also were to raise your hand. So you may see at the bottom of your Zoom screen, there's a little hand and you can raise it, and that will actually ping me to introduce you, and I can actually share your video or your audio, and you'll be able to interact directly with Michael and myself. So feel free to raise your hand. It looks like one person already is, but Braden, we're gonna let Michael get started before I start taking questions on there. But don't worry, please do raise your hand in the future. I'm happy to promote your video and your audio. One thing to know is that the video for this session is being recorded. So that means that we're going to be posting this on our archives on our website. Kingdom Access Television will also be broadcasting each of these classes the day after they're on our website. So feel free to let your students know that they can watch on television too, should they have any trouble with the internet or with accessing us on any of our other means. So once again, I just wanted to welcome everybody. We're really, really happy to have you here today, and I will turn things over to Michael.
Okay. Hello, everybody. Again, my name is Michael. I'm a science educator here at the Fairbanks Museum. And today in this class, we're going to be discussing energy, particularly what energy is, where it comes from, and in specific, how energy is created and used here in Vermont, right? Vermont actually has an incredibly interesting and really kind of cutting edge history with energy. So it's going to be really quite an interesting topic. So hold on, I just have to adjust my screen. Okay, that's perfect. Excellent, great, thank you. Okay, so before we begin talking about how energy is used in Vermont, which is probably particularly interesting to us, today in times of worry and trouble, it's important to know where our power comes from. How do we get it? Is it stable or not? Are we going to have it indefinitely? These are all important questions. But before we talk about that, it really takes a little bit of thinking to understand exactly what energy is. If somebody asked me today to explain energy in a single sentence, I would kind of have to struggle to do it. It's a little bit of a difficult concept, even though it's something that we use every day, of course. So whenever we talk about a difficult concept like energy, I always like to start talking about the word itself. Where does the word energy come from? What does it mean? It's a Greek word, and it comes from two separate Greek words put together. The first is En, of course, which means inside or simply in. It's where we get our word in from. And the second word is ergon, which E-R-G-O-N, literally means work. So the word energy means the work inside. So the work inside what? It refers to the work that is inside of any material substance. So if you were going to go in a dictionary and look up what's the definition of energy, it would probably tell you something like the ability of any kind of material to perform work. Now that's still probably a little bit confusing, but think of your own body as an example. So of course, we all know that our muscles are a part of our body that help us to perform work. right? We can lift things, we can breathe, we can speak, all because of our muscles, right? Our muscles are a material that have the ability to perform work. So that's pretty simple. But that's only one kind of energy, right? There are a couple different types. When we talk about our bodies moving, our muscles stretching and flexing, burning nutrients, oxygen, and water in order to work, that is a kind of mechanical energy, right? Mechanical like a machine. Our bodies work like a machine. Our muscles can flex to move objects, to move our own bodies, all of that. But there's other kinds of energy, right? Another simple example is the kind of energy that we use every day to cook our food, right? Of course, we can't cook food with mechanical energy. You can't stand over a steak and smash it until it's cooked and ready to eat. We have to use heat, right? Thermal energy or heat energy is simply another kind of energy. And there's many ways that we know to create heat, right? Think about wood, for instance, as a material that has heat energy inside of it. So remember, energy being the work inside of something. Wood, we know, has the power to burn, to release heat, and help us do work by cooking food, for instance. So we have mechanical energy, heat energy, but also another one that we experience every day is, of course, light energy. You guys know that if you go outside, maybe not today, but especially in the summertime, and if you sit out in the sun, what's going to happen to you? Your body is going to heat up from the heat, of course, that's coming from the sun, but also we're going to get sunburned eventually. That burn that we experience on our body is literally the light energy, the wave lengths of light. Light is a complicated thing that we're not really going to talk about too much today. But that energy from the moving light waves hits our bodies and actually really cooks our skin cells. So the sun's light is doing work on our body when it kind of cooks us, right? X-rays are another kind of light energy, radiation energy. And of course, we know that X-rays are quite dangerous, right? When you go to the doctor's office to get an X-ray, which is that black and white, picture of your internal body, if you've never had an X-ray before, you have to wear a lead vest, a lead covering to protect your body from those harmful X-rays. X-rays kind of give you like a sunburn on the inside of your body. They're kind of a strange thing. But so those are three beginning types of energy. And it looks like we have a question here. What is our question, Drew?
So, Michael, we have one person asking, is there energy in space? Outer space, I guess you could say.
Yeah, in outer space, there is quite a bit of energy in outer space. That's exactly right. We just talked about light energy, right? Of course, we see the light from the stars, which are other suns way out in outer space. Even just here from Earth, if you went out in outer space without a spacesuit on, there's actually so much radiation energy, so many X-rays, so many gamma rays, so much light that it would be very dangerous for you to be out in space without any protection, because all of that energy would destroy your body almost instantly. There's actually a lot less energy here on Earth than there is just floating out in outer space. So that's a good question. Yeah, you would certainly die from all of that energy, right? So we spoke about mechanical energy, like your body, heat energy, like burning substances, like burning wood, and light energy or radiation energy. There's just a couple other types that we maybe don't see so often. Another type is chemical energy. If you've ever seen a chemical reaction where you take maybe baking soda and vinegar, or two substances that by themselves are maybe a liquid or a powder, not doing anything on their own, you put them together, they might spontaneously create energy. They might boil, they might explode. Those chemical reactions are microscopic changes in the actual chemical makeup of those objects. That's a little bit complicated. We won't talk too much about chemical energy today. Also, nuclear energy, we'll talk a little bit about that later. I'll save that one for now. Do we have another question?
Sorry, unmuting myself. We have actually a few questions here, Michael. So one is, one person would like to know, is there energy in air, like the stuff we're breathing around us? Or does, I guess maybe you could interpret the question as, does air convey energy?
Yes. Yeah. So especially when you're talking about, for instance, wind, we've all felt the mechanical energy of wind pushing against us. Think about, for instance, how a sailboat works. A sailboat is powered by wind energy, by the mechanical energy of wind. Same thing with a windmill, which we'll actually end up talking about a little bit later. So that's good. Do we have more questions, Drew, you said?
Yeah, so another good one. I guess this person's probably thinking about, is there energy everywhere is their question. I think what they're wondering is, are there places where maybe energy doesn't exist?
So that's an interesting and good question. What we would say is that pretty much any physical object has, this is tricky, has potential energy, right? So when my body is moving, for instance, when my muscles are working right now, they are expressing, is kind of a way that we talk about it, mechanical energy, right? And when my body is doing that, we call it kinetic energy, because it is moving and it is creating energy right now, right before your eyes. But think about a rock that's sitting on top of a mountain that's not moving at all. It isn't expressing any energy itself right there if you just look at it, right? It's not moving itself. It's not on fire. It's not spontaneously exploding or anything like that. But we would say that that rock actually does have potential energy. What does that mean? So that means that, of course, over time, as that mountain erodes, that boulder that's sitting up on top of the mountain, what's it going to want to do? It's going to want to, of course, slide down the mountain to the bottom. The boulder has the potential to move and express a lot of energy as it rolls down the hill. Every single thing on the whole Earth right now is being held down by a very powerful type of energy that we call gravity, right? The reason that me and all the objects in this room aren't floating up towards outer space is because the rotation of the Earth actually creates a kind of unseeable, invisible energy that's pulling us all down towards the center of the Earth. So if I jump up right now, the reason that I fall back down to the ground is because the energy of gravity is pushing me down towards the ground. So every single thing, every single object is being pushed on by gravity, and it has energy in that sense. Even stuff in outer space is being pulled around by gravity. That's how our solar system works. So yeah, I didn't hit my head. I saw that comment. I did not hit my head. The ceiling's not that low. Yeah, so, okay. Before we really begin to talk specifically about Vermont's energy, I have to set up a bit of an experiment here that you guys will see. I have to do this on the table for this beginning part because I don't want to set my carpet on fire. But this machine here is a miniature steam engine. This is the type of machine that human beings all across the world and all throughout recent history have used to create and harness energy. We can harness our body's energy very easily just by moving our muscles, but it would be very hard for us to run an entire factory or something like that, for instance, just using our own human energy. So we have to figure out ways to take energy out of the environment and harness it, kind of like you put a harness on a horse to use its energy. We have to figure out how to harness the energy that's all out in the environment to do work. The steam engine is one example of that, and we'll be using it in a minute. But in order to get it start to work here, I have to light it. If you know anything about steam engines, and we'll talk a little bit more about them just in a minute, we're going to use thermal energy from a burning substance, maybe coal, maybe wood. Here we're actually using alcohol fuel. And we're going to turn that heat energy, that thermal energy, into mechanical energy. So that's set up now. But this is going to show us the most the most amazing thing about energy is that you can take any of the types of energy that I mentioned: mechanical energy, chemical energy, heat energy, light energy, radiation energy, electrical energy, which we'll be able to see in a little while, and you can actually turn any one of them into any other type of energy pretty easily. That's kind of a hard thing to imagine or think about, but the steam engine here, once it gets going, is going to be a very good example of how energy transfer works. Another very simple experiment that you could do at home to show how energy can transfer is to put on fuzzy socks and shuffle your feet around on the carpet very, very fast. I'm sure you've all done something like this before, and you'll know that the effect is when you rub any two things together fast enough, you could take your hands and rub them very fast. You're using mechanical energy to rub your hands together, but eventually, as you continue doing this, what will you begin to feel? You'll begin to feel heat building up between your hands. We call this friction, of course. You've heard of this before. Same thing that happens when you get a rug burn. If you're running in your house and you fall down and you get a burn on your legs, that's friction. You're turning the mechanical energy of your hands moving into heat energy. If I did this fast enough, my hands might burst into flame. I can't move them that fast, but the steam engine can move quite fast, and I'll show you how it can transfer energy in just a minute. If you put on fuzzy socks and shuffle your feet really fast, you'll be able to feel them get warm, but of course, what else will happen when you shuffle your feet in socks? If you go and touch a doorknob then, or if you go and poke your sibling, you'll give them a static shock, right? The reason that happens is because when you take two surfaces, usually if one is fuzzy and one is smooth, that's often how it works. Like if you rub a balloon against your head, this is kind of complicated. All atoms, which is what everything is made up of, have electrons, which are essentially electric charges that are a part of those atoms. If you take two objects where one of them is relatively smooth and one of them is not very smooth, kind of fuzzy, and you rub them together, you can actually move those electrons between the two objects. That's why if you take a balloon and rub it against your head, the balloon will stick to your head because you have actually electrically charged the balloon. Now, if you rub your feet on the carpet, you'll electrically charge your own body by stealing electrons, or really by taking electrons out of your fuzzy slippers and putting them into the ground. And then if you touch an object, you'll get a zap where your body is evening out its electricity. We're not going to talk too much about that today because it's kind of a complicated subject, the way that electricity is generated. We'll get into it a little bit more a little bit later. But so if you rub your feet on the carpet, what you're doing is you're taking mechanical energy and you're turning it into heat energy through friction, and you're also turning it into electrical energy just by swapping electrons around. So that's how that's how energy can transfer between the different forms. Do we have a question, Drew?
Yeah, so we've got a whole bunch of questions here, so I'm going to try to do as many as we can, but I want to keep Michael going on his experiments too, so I'll just ask two to start. One is, one person asking, how much energy do we have? You know, is there some kind of estimate for the entire, I guess, world, or is it universe? I think you could take it at whatever level you want, Michael.
Wow, that's a very tricky question. That's right. So here's the interesting thing about energy. If you've ever heard of the Big Bang, it was a massive chemical energy explosion that happened in the extremely distant past, millions upon billions of years ago, and that created the whole universe. It basically created all material, all elements, and it also created a whole lot of energy, an extreme amount of energy. All of the energy, this is very hard to understand, but all of the energy that is around us today, all of the mechanical energy, all the heat energy, all of our body's energy, all of the sun's energy, that's all leftover energy from that Big Bang. It's an unthinkable amount of energy, but eventually it will run out. You may have heard, this is a concept that I really don't even understand myself. But in an extremely long time from now, the universe is actually all going to cool down. The energy of the whole universe is going to run out. It's pretty sad, right? All the energy that we're using today to move our bodies, to light our homes, to heat our homes, that's we're all using the energy of the universe, and eventually we're going to use it all up. People call that the heat death of the universe, which is a terrible sounding thing, right? But humans don't really have to worry about that. But it's a complicated answer to your question. That's kind of the best that I can do.
Yeah, and I would just add that, the first law of thermodynamics says energy can't be created or destroyed. So when we're thinking about that heat death, it just means the energy is becoming heat. So it's not useful energy in
right. Oh yes, yeah. It can't be used. It's dissipating out into the universe, and we're not going to be able to use it up anymore. Right?
Yeah. And Michael, there's a bunch of questions coming in, and I want to make sure that you can get to your experiment. So I'm not going to ask you other ones from the Q&A right now. Don't worry, guys. If you're posting on the Q&A, we'll definitely get to those. But I do want to give Braden, who's been raising his hand since the beginning of our meeting, a chance to share his audio and his video if he wants, and to chat with you for a moment, Michael. He has a question, I think, that he's been waiting to ask. And Braden, you'll get a ping on your end to accept. Here he is. So Michael, Braden, I just want to make sure we unmute you. Here we go. When you're ready, why don't you ask your question?
Hi.
Hey, Braden, we're having a little trouble.
What is energy?
What is energy?
Yeah, great question.
Yeah. In a very simple way, energy is the ability to change things around you. That's kind of complicated. There's a lot of different ways to change things, right? By moving them, by heating them up, by giving them an electric charge. Energy, you can think about it as energy is work. And anything that can be changed or worked on shows us that energy shows us energy. Energy itself is like an invisible kind of thing. Yeah.
And one question maybe we can add on, since you're on the topic, Michael, somebody else asked, what is energy made of? If we can think of it that way. I know you're going through the different types already.
Right, yeah. Energy is not a thing. Energy is not something that you can pick up and hold and touch. In the past, 100, 200 years ago, scientists actually did think that maybe energy was a thing. They thought that it was an invisible fluid that was flowing all around us. But since then, we've come to learn that energy is not a physical thing. Physical things can express energy. It's kind of, it's a very, very tricky thing to think about, but think about it this way. Your words, when you speak, your words are not physical things, right? But they do have an effect. People can understand your words, and you can change things through speaking. You can tell somebody to do something, and they will go and do it. Your words aren't, you didn't throw your words at them and force them to do something. That's kind of how energy is. That is a very difficult question to answer. Any other questions?
So we have a lot of other questions, but I'm going to let you keep going, Michael, so that we can get through some of class.
Okay. Let's see if my steam engine has warmed up enough here. It seems like it keeps going out. Oh, geez. Oh. Hold on. I have to refill the alcohol on my steam engine. That's too bad.
Okay. Do you want me to ask you a few questions while you're doing that?
Yeah, you could ask me one or two. This will only take a moment.
Okay. We have Willa asking, are some types of energy visible? Could you see them, in other words?
So light energy is a good example of that. All the visible light that you see coming out of the sun, for instance, like a rainbow, is the light from the sun that gets split up by water vapor in the sky, and it lets you see all of the different visible colors. That light energy is visible to us as a light ray, as a beam of light. When you turn on a lamp or a light in your house, you can actually see that light energy. It literally brightens up the room. That's probably the best example of it. You could also see heat energy, particularly like when you're cooking or when you're heating anything up. If you heat up a piece of metal, for instance, you can see it turn red as all of the molecules in your pan get extremely, extremely hot, right? That's another way that you could see energy. Yeah.
Do you want another question, Michael, or are you thinking about getting the experiment going?
You can do one more.
Okay. Actually, we have Cooper who wants to share his screen with you.
Okay.
He's going to ask you live a question.
Great.
And Cooper, you just need to click to accept the offer I gave you, and I'll unmute you. So Cooper, when you're ready.
Hi. How does energy move?
How does energy move?
Yeah.
Right. So energy itself doesn't really move, but we can move things with energy, right? What's a good example of what you're thinking about? So when you think of electricity, you think of electricity moving through power lines, right? Going from the power plant where that electricity is made to your house where it's used. That electricity is actually little electrons, little charged atoms that are moving through that power line extremely fast to your house through the socket in the wall in your house into the lamp, and inside of your lamp it's turning from electrical energy into light energy so that you can see it. That's an example of how energy can move, right?
Thank you.
You're welcome. Okay, it looks like this is beginning to boil here. Okay, we'll give that just one more minute. So to introduce you really to the second part of this class here, we're going to be talking about the history of energy in Vermont. When people first started to harness energy back in the early colonial times here, when the settlers first started to build things for themselves, to build factories and things like that, there was no electricity. Certainly, we didn't know how to harness electricity yet. We had to use the mechanical energy from our own bodies. But of course, you guys also know that people used animals and their energy, right? If you take two horses and you strap them to your cart to pull it across a road, they have much more mechanical energy than you do because they're bigger, stronger animals. And so it's better for them to pull your cart than for you to pull the cart, of course, right? But people are very clever, and we came up with different ways to get even more energy. If you've ever seen a water wheel, an old water wheel, out in a river, you might see that it uses the mechanical energy of the moving water. That's another example of energy moving that you can see. If you see waves or moving water, you can tell that that water has force moving, and you can use that moving water to turn a water wheel. And then usually that water wheel will have a crankshaft that's connected to maybe a saw on a lumber mill, or maybe a big grinding wheel on a grist mill or something like that. You can use the power of a moving river to move very large machines, like a gigantic lumber saw that might be this big, a giant circular saw, right? Eventually, more complicated energy-making machines were discovered. So as I bring this up to you, I have to be very careful with it. Oh, I have to go get my... It's all very hot, so I have to touch it using the pliers here, but I can lift you can hear the whistle there a little bit. I'm going to open the valve, and you have to get this guy started a little bit. You can see it's going extremely fast. We'll let it run out here. But what you guys are seeing is that transfer of energy that I was talking about before. We are using thermal energy from the burning fuel, burning alcohol, to heat up water that's inside of this tank. That heating up water is boiling. And you guys know, if you've ever boiled water before, as it boils, it turns into steam. That steam wants to rise, right? You can see steam rising out of a boiling pot on the stove. It's rising out of the tank here, going through this tube. That tube connects right here into this piston. The moving steam pushes on this piston in and out to turn that wheel. Wow. Oh, I'm getting my computer all wet. Wow. That's super fast. We'll let that run out.
How's your computer doing?
That's a little wet, but that's okay.
Okay. So I'm going to promote a few more of our folks in class to ask some questions. Molly has been having her hand up for a while. Molly, when you get a ping, please accept the invitation. Oh, hang on. I got to unmute you. There you go, Molly. Feel free to ask away.
What happens? Does something happen when two different energies mix?
When they mix?
Yeah, like they get put together.
Like, this is an interesting question. So two different types of energy, you might think that because they're all energy, you could put them together and then get double the energy, right? So if I had the same amount of mechanical energy, maybe if I had, let's say, if I had a fire with me that produced the exact same amount of energy as my muscles did, and I put them together, I'm not going to get twice as much energy. But what you can do, like what we were using this steam engine to do, is you can take that fire and convert it into mechanical energy like we were doing with the steam engine, and then add it to my physical energy, and then you can get even more energy. So that's the interesting thing about it. You can't make two different types of energy add up on top of one another, but you can always convert mechanical energy to chemical energy or chemical energy to thermal energy, and then you can make them add up. So that's kind of how it works.
Oh, cool.
So Michael, we have a bunch of people with their hands raised, and I'm going to share their questions in a moment. One person keeps wanting to know, does energy take up space? And this is akin to the question we had earlier, whether energy is, consists of matter or not as well. So maybe we can talk on that while I promote somebody else to ask a question. Right.
Yeah, I know that this is a very hard thing to kind of wrap your head around. Even I don't really have my head wrapped around it. But energy, so only physical things that you could touch or feel take up space, right? Things that have a body, right? Energy itself doesn't have a body. It isn't a physical object. So it can't exactly take up space, right? That's
Yeah,
yeah.
that's a good answer. I'm gonna unmute John now. He's sharing his audio, and I think he had a question too.
Okay, let's hear it.
Actually, I accidentally hit raise hand, so sorry.
Okay.
That's okay. Well, we got plenty of questions here, so I'm gonna allow somebody else to talk. It looks like S Ging is the screen name. So I am adding you, S Ging, and I just unmuted your audio, so feel free to ask a question. Oops, it lets me unmute. I think you have to accept my invitation to share your audio first. Okay, well, I can't get S Ging to work, Michael, so I'm just gonna promote Grayson, and he can ask a question. And Grayson, make sure you click on to accept my invitation before you start talking. Here we go, Grayson, when you're ready.
How fast can energy move?
How fast? Well, yeah, that's a good question. So we talked about light energy before, right? The light that, for instance, comes out of the sun, or the light that you can make with a light switch in your house from a light bulb, right? Light, in fact, is the fastest thing in the whole universe. It's impossible for anything to move faster than light can move. Light moves at 186,000 miles per second. That's super fast. If you could run 186,000 miles per second, you could run laps around the Earth in just a few seconds. So light energy is literally the fastest thing in the whole universe. Electrical energy moves not quite as fast, but you can also get electrical energy to move extremely, extremely fast. The electricity that's made in a power plant, maybe 50 miles away from your house, can be sent through high tension power lines and reach your house in a matter of seconds, because it can move so fast. But again, so this is the super tricky thing. Again, it isn't like energy is a physical thing that's moving through the power lines. The energy is being carried by electrons. Or in the case of light energy is being carried by the light wave moving through the air. Those are very tricky concepts, kind of like high school, college level concept. So you don't have to necessarily have a full understanding of that right now, but hopefully that helped.
Yeah, and I just wanted to mention, I've been answering a lot of our questions in the Q&A in text form. So guys, if you've been asking questions on there, make sure you read the answered part where there might be some text answers for you. Michael, maybe before we go on, I'm going to promote one more person to ask a question, if that sounds good.
Okay, yeah.
And this is Willa that has been waiting to ask a question.
Okay, I will.
Oh, Willa, my fault. I just had to unmute you. Now feel free to ask your question.
Do we need energy to survive?
Ah, very good. So I'm sure that you've heard that you have to eat food and drink water to fuel your body. Otherwise, of course, you guys know what happens to you after a few days without water or a few weeks without food. Your body will die, right? The reason that it dies when you don't have enough food and water, again, your cells, the things that make up your body, all of your organs, they require oxygen, which we breathe in from the air, water, which we drink, and the nutrients from food in order to run, in order for them to work. They're kind of like, you think about them like your car, right? The engine in your car needs gasoline to burn. If your car runs out of gasoline, the engine dies, it doesn't work anymore. If you don't breathe, drink water, or eat food, your cells run out of fuel. And for instance, think about what might happen to your heart after its cells run out of fuel, or your brain, or your lungs. Those organs will slow down and stop working. And of course, that kills you, right? So, good question.
We have one more person. Cooper's wanted to ask a question, so I'm going to promote Cooper now.
Okay. Hi, Cooper.
And let me just unmute Cooper. I hope you're still there.
It's a little tricky. Yeah.
Yeah.
So, if like the energy can move that fast,
Mhm.
how fast do you think the energy would move if it would have like been if you combined two energies that were the same, but they were both going the same like miles per hour? When they like hit each other, would they like do something weird? Like if like there was one energy in a power line and another energy in a power line, and they're both going really super fast, and then they run into each other, will they do something weird?
Yes. So using the using charged atoms moving through a power line is kind of a hard example to imagine in your head. But think about two cars driving on a road. If a car is driving and it drives at 40 miles an hour into a wall, that crash is going to create a lot of mechanical energy, right? The car is going to crumple, car parts are going to fly everywhere. It's going to be bad. And you can see it's going to make a lot of noise. Sound is often a great indicator of how much energy there is in an event. But so now think about two cars both going 40 miles per hour, hitting one another like this. Is there going to be more energy?
Would there? Yeah.
Yeah. It's going to be the energy of the impact is going to be higher because both of those cars both had their own energy. 40 miles per hour in this car, 40 miles per hour in this car. When they hit, the resulting sound and crumpling of the cars and flying of material is going to be greater than a car hitting a wall that isn't moving. So you are right. If you take two objects with energy and you make them collide, or you put them together, you can, what's the best? You can increase the amount of energy. But again, it has to be energy of the same form, right? So both those cars moving, that's motion, that's mechanical energy, right? So does that answer your question?
Yes.
Good.
So, Michael, maybe we should keep going with class. We're just under 20 minutes. So we've got a few more questions, but I'll hold on to them till the end.
Okay. So we spoke briefly about Vermont's use of energy in the past. People learning how to take the energy of the natural environment, whether it was the animals that they owned or the moving water that might be on their property, and use it to do work, right? The kind of next step in that process is, of course, things like the steam engine, where people learned that they could burn certain materials that were good at burning, like wood, like charcoal or coal, or like oil, in order to create a lot of heat all at once, and then convert that heat into mechanical energy by making that heat boil water, forcing that water through a piston, and making that wheel turn, right? By using a machine like that, you can create even more energy than you would be able to by just putting a water wheel in a river. Using a machine like this, you can control how much energy you're getting out of it by putting more burning material into the fire to make a hotter fire, to boil water faster, and then to get more energy. As you saw, that creates a whole lot of energy. When you're talking about a river, you can't control how much energy the river gives to you. Unless, well, you can by building dams or by changing the flow of the river, which people began to do. But even as people were building steam engines like this, people started to dig, for instance, fossil fuels out of the ground. If you've ever heard of fossil fuel, you might know that coal, natural gas, and also oil are the three primary fossil fuels that we talk about. We call them fossil fuels because they're organic material deep underground that was formed millions of years ago. Think about how we find dinosaur fossils. and they're from millions of years ago, of course, that fossil fuel, that oil and coal underground, is actually the organic bodies, the decaying, very old bodies of ancient plants and animals from millions of years ago. So the oil, for instance, this is a jar of crude oil from Canada. This is what people drill out of the ground. This is basically a slushy, dark, oily little mixture of the ancient bodies of plants and animals that used to be living on the earth, buried deep underground. It burns very, very well. It makes for really great fuel. And it's also very useful because this oil can be turned into all different kinds of helpful substances. All of these guys here are jars of different things that people make out of oil, that fossil fuel. Not only gasoline and diesel fuel, but also other helpful things. I'll just take a couple of them here. We use every day. For instance, any kind of lubricating oil that you use in an engine or anything like that. This is engine oil, machine oil. You guys all have something like this in your cars. If your parents work on machines, work at a factory, work at a car shop, they're working with this stuff all of the time. We need oil to make this stuff. Oh, that's okay. Also, any kind of paraffin wax. Most of the candles in your house, here's a paraffin wax candle, are made out of this fossil fuel oil that we dig up out of the ground. Also, very similar to this paraffin wax is petroleum jelly, also made out of oil, and Vaseline is mostly petroleum jelly. Any kind of lip balm that you use is mostly petroleum jelly. So this stuff, this ancient old animal and plant goop that we're digging up out of the ground is used to drive our cars. It's used to build pretty much all plastic that we have today is made out of oil, and it's also used for beauty products and lip balm and for candles. All this kind of stuff, we rely on oil to make. But you guys might have heard that we are, depending on how you think about it, unfortunately, running out of this oil. It takes about 50 million years for fossil fuel oil to form underground. And we've almost used up all of it. So if we use up all of the Earth's reserves of this oil, it's going to take another 50 million years to get another supply of it. We're going to have to wait 50 million years for the Earth to form more oil deep underground. So once we run out of it, not only are we not going to have the same kind of gasoline and fuel that we're used to burning to heat our homes, to drive our cars, but we're also not going to have all of these petroleum products, like a lot of beauty products, candles, a lot of wax, all plastic. Think about all the things that we have that are made out of plastic, right? We're going to have to think of different materials and different fuels to use in place of this stuff. And Vermont, thankfully, is actually one of the leading states in terms of using less of this fossil fuel and using more what we call renewable energy. You guys have probably heard of renewable energy before. You guys have probably seen the wind farms that are up in Caledonia County, and I think that there's one also in Orleans County and in Washington County. The Sheffield Wind Farm is one that I had the pleasure of going to visit. Those windmills are producing electricity in a very similar way to how water wheels can produce electricity. The wind is turning those big windmills, and as those windmills turn, inside of there, it's turning a turbine. And as that turbine, this is kind of complicated, but as that turbine turns, inside of it, there's a little magnetic coil, which is turning. And that magnetic coil is turning inside of a ring of other magnets. And that's kind of complicated, but think about it this way. If you have two magnets that are lined up north to south, they want to attach to one another, right? And if you pull them apart, it takes a little bit of force to pull them apart, of course, right? By doing that, by pulling magnets across one another, by pulling them apart, by putting that little bit of force to turn the magnets, you're actually creating what we call an electromagnetic field. Basically, when you turn magnets close to one another, it creates electricity. That's crazy to think about. That whole concept, we do a whole nother class actually about electricity, where I talk about that more. But we don't have time to talk about it right now. But that's what those windmills are doing. They're creating electricity just through the power of the wind, the mechanical energy of moving wind, turning the turbine. The turbine is taking that mechanical energy, turning it into electrical energy, and sending it to your homes. That kind of energy is infinite. Hopefully, there's always going to be wind in Vermont and on Earth. And as long as there's wind and we can keep those windmills running, we have an infinite supply of energy. Now, keeping those windmills running is actually a very difficult thing, as it turns out. They're complicated machines. So it's hard to go from using fossil fuels like this to renewable energy, but Vermont is doing a very good job with that by building these windmills. And also, if you've ever driven up 91 between Barnet and, actually maybe it's south of Barnet, but between Barnet and St. Johnsbury on 91, if you look off to the side of the highway, you might see that large power plant that's usually billowing lots of white smoke up into the air. That's called the Rygate Power Station there. And it's a lot like the power stations all across the country that are burning oil or coal to make their energy. But that power plant is kind of actually very special, very high tech. What they're burning in that power plant is actually wood chips. And now that might not seem very high tech. People in Vermont have been burning wood for heat and energy for hundreds of years, right? But that factory is burning actually mostly wood chips that are the byproduct, that are the leftovers from other people who are cutting down lumber in Vermont. People who are cutting down lumber for paper, for wood pulp, for all different kinds of things. In their sawmills, they create a lot of sawdust, basically, leftover wood chips. A lot of those they can't really sell to the paper factory. Instead, they take it and they sell it to the Rygate Power Station, where they burn it and turn it into electrical power in a similar way to how that steam engine works over there. The wood is being burned to boil water to turn it into steam, again, to turn a turbine, which turns an electromagnet, which creates electricity through the electromagnetic field, right? Do you have a question, Drew?
Yeah, so we have actually a few questions in our Q&A and then a bunch of people with their hands raised. So I think I'll just do the Q&A questions first. And we have about, I don't know, I'd say 7 to 8 minutes left in class. So we can maybe take questions to the end of class. We'll see how we do. And then maybe I'll turn it back over to you, Michael, for some last thoughts.
Yes, okay.
First question is, atoms have energy, right? What do you say?
Atoms are a scary subject for me. So when we talked about gravity, right, which is this invisible force that's created through the mass of our planet and all the moving bodies in space. Our solar system is a bunch of big round objects that are orbiting around the sun, because the sun is the biggest object around us and has the most gravity. If you think about an atom is basically something like a solar system in miniature, right? Inside of an atom, there is a central packet of protons and neutrons that have a little bit of weight, and around them orbit electrons, just like the planets orbit the sun in our solar system. But inside of an atom, it's not gravity that's making those electrons orbit the protons and neutrons, but instead we call them the strong force and the weak force. They're forces they're energetic forces like gravity, but we don't really understand, well, at least I don't understand, how exactly they work. So yes, atoms do have electrical energy because of the protons and the protons and neutrons that make up atoms. They do have electrical charge, but then also there's another kind of force that's like gravity holding them together. And I don't really know how to explain much more than that about strong force and weak force. That's like certainly college level stuff. So
you guys are definitely thinking along the right thoughts and are way advanced, but definitely a good topic for that we can tackle in a future day, and that you can do some research on the internet. A few more questions from our Q&A, Michael, and this is returning to what you were talking about with fossil fuels and renewable energies in Vermont. Willa asks, is Vermont helping the environment because we are not using oil for our cars or other fossil fuels instead of in favor of these renewable energies?
That is exactly correct. Yeah. By using, well, first of all, when you burn, I forgot to mention this before, but when you burn fossil fuels, oil like this, gasoline in your cars, charcoal, whenever you burn those fossil fuels, they release carbon dioxide into the atmosphere. Now, there's already a little bit of carbon dioxide naturally in the atmosphere. But that carbon dioxide is what we call a greenhouse gas, which basically means that the more carbon dioxide gets in the atmosphere, this is kind of complicated, but the more carbon dioxide, the more methane, the more ozone that gets into the atmosphere, the warmer our planet is going to get, basically. Those gases, that carbon dioxide that floats up into the atmosphere, basically makes a big blanket around our planet, and it insulates the planet. It keeps it warmer than it should be. And that's part of what causes climate change. And that's the part that humans are responsible for. So when we get our electricity by using a windmill, for instance, we're not putting any of that carbon dioxide into the atmosphere because we're not burning anything. So that's very healthy for the environment. That's very helpful. And also when we're talking about like the Rygate power station where they're burning wood, when you burn wood, it is certainly true that you are putting carbon dioxide into the atmosphere. But when you're burning trees, you can replace the tree that you burned within 50 years. The people who are cutting down trees in Vermont, by law, they have to also replant a certain number of trees to make up for the trees that they're cutting down. And it takes a tree only about 50 years, a hardwood tree, 50 to 100 years to reach maturity. And then so you're replacing the tree that you cut down and burned. Fossil fuels, on the other hand, if you remember, take 50 million years to replace. So that's 1 million times difference. Also, trees suck carbon dioxide back out of the atmosphere. So if you're burning trees to make power, as long as you're replacing them, you're putting that carbon into the atmosphere, but then taking it back out. And you're making a kind of cycle. And as a result, it's much, much, much healthier for the environment than burning that fossil fuel and just putting tons of greenhouse gas into the atmosphere. So Vermont is doing a lot of work to make our air and the rest of the environment healthier. Yes.
And one more question from the Q&A that Way is on, I guess is the name, is keep asking. And just to tie it all full circle for today's class and back to the points you were just making, does pollution have energy? What do you say? And then we can promote a few people to ask their questions live as we wrap up today.
So this is a very cool thing. So when we think about pollution, we think about air pollution, certainly, which is what I was just talking about. That the CO2 and methane and ozone that we're putting into the air, the reason that it works like a big blanket around the Earth is that those molecules can actually trap a lot of heat energy that's coming from the sun, and they can get very warm and stay in our atmosphere. And that's what kind of makes that big warm blanket around us. So in that way, yes, that pollution, that air pollution, can hold in a lot of extra energy, and that's bad for the environment. However, we can also look at it kind of from another angle. If you think about compost and food waste, for instance, people now, especially in other countries, are coming up with ways of taking your compost and your food waste and turning it into biofuel. What they make are these little machines that I don't know how to call it. It's like a sealed container with special microbes inside of it, and you throw your trash into there, and the microbes eat away at your trash, and as they decompose and compost your trash, they give off a kind of gas that you can then use for fuel in your home. So you could imagine in 20 years in Vermont, everybody could have these little machines in their homes. You put all of your food trash into these machines, and the machine turns your compost into fuel. So then your stove runs on your own trash, and your house is heated by your own trash. So we can actually use pollution, garbage, trash in really helpful ways to make energy again. So that's hopefully in my lifetime and in your guys' lifetime, we'll be able to see something like that in every house in Vermont and all across the United States. Yeah. Any more questions?
Yeah, sorry, I'm just promoting Reese. She's been waiting for a very long time to ask a question. And Reese, I'm just going to unmute you. So if you want to ask your question.
In any way?
I'm sorry, you're going to have to say your question again because you got cut off.
Can you feel energy in any way?
Yeah. So again, it's hard concept. You can't like touch energy itself and say like, oh, I'm holding energy right now. But you can feel the effects of energy, certainly. If your sibling kicks you, you're feeling the effect of mechanical energy. If you burn your hand over a fire, you're feeling heat energy. If you get a static shock, you're feeling electrical energy. So you can feel energy in all of its different forms. You can feel your face getting sunburned by the light energy from the sun. You can hear sound, another type of energy. So yes, we're feeling energy all day long. Yes, that's your answer.
Okay, and I've just promoted John, who's sharing his audio, to ask a question. We've just got a few more questions before we wrap up.
Okay.
And this is John. So John, feel free to ask your question. Are you there, John?
Did you unmute him?
He is unmuted, yes. I'm going to promote S. King to be asking questions too. So S. King, if you want to ask while we wait for John, I will unmute you. It looks like there's a teddy bear for your video.
Sometimes on Zoom, you have to manually unmute.
Yep.
Oh, if considering we're in quarantine, are we using more energy or yet less?
That's an excellent question. So thankfully and interestingly, people in Vermont per capita use less energy than people in almost every other state in the country. So that means that Vermonters are thrifty with their energy in the first place, which is good. On the other hand, because people are staying home much more, we are using certainly more electrical energy. All day long when people are at work, hopefully you turn off your lights in your house. You don't run all of your appliances all day long while you're at school and at work. So energy consumption is low at home during the day. Now that we're all at home, we're using much more of that electrical energy. But on the other hand, people are driving their cars a lot less. So we are burning less fossil fuels in the engines of our cars. So it is kind of a give and take. We're using more energy in some places, like in our homes. We're using less energy in other places, like in our businesses, factories, and in our cars, right? So that is a good question.
Yeah, and I just want to ask, let Willa ask our final question for class today. We're a few minutes over our end time, but I wanted to make sure we got all these good questions in. So I'm going to unmute Willow right now, and you can ask your question.
Do we create energy? And if we do we create it even when we're sleeping?
Yes. Yeah, good. That's a great question. I didn't really talk about this. So, yes, the answer is yes. When we're sleeping, of course, most of our organs are still working, right? We're still breathing, our heart is still pumping, our stomachs are still working. All of our organs are really still working. All of our cells are still working. So we certainly are expending energy, right? Even when we're sleeping. And also, you can tell that you're expending energy because even when you're asleep, you're still quite warm, right? We're warm-blooded animals, which means that a lot of the energy that we take in from food goes into keeping us warm. But heat waste is one very good way to tell that energy is being used. For instance, in your own body, when you go running or you go and work out, of course, you sweat and your body gets very warm. It gets very hot. Pretty much all kinds of energy, when it's used, creates waste heat. When your muscles work really hard, they warm up, of course. When you move your hands together really fast and create friction, you're creating waste heat just through that friction. Even those, the windmills that I mentioned a moment ago, as they turn, they actually get hot. They actually get warm inside of all of their mechanical parts because of the energy that's being created and the waste heat that's coming out. So yes, you are always, always, always using, creating, expending energy. Yeah.
So Michael, we had a desperate plea for one more question for you to answer. So this is S. King coming back one more time.
Okay.
And then we'll wrap up our class for today.
Sounds good.
Okay, so if your energy, does it ever run out?
Does it ever run out? So so we talked about how in our human bodies, we can run out of energy if we don't put enough fuel into our bodies, right? Our bodies run on oxygen, water, and the nutrients from food, right? So our bodies can run out of energy, but one of the main laws of physics, one of the main truths about our universe is that you can't destroy energy. Energy can't go out of existence. It can move from place to place and from type to type between mechanical, thermal, chemical. But you can't like kill energy. It's so hard to talk about energy because it's not really a thing, right? But so like before, when we were talking about the beginning of the universe, when all of this energy first got sent out from the Big Bang into all of the different planets all throughout the entire universe, and it is being used, but eventually it's all going to kind of run out and it's going to escape as heat, and then everything is going to be cold and there's not going to be too much energy left in the universe. So energy can't be destroyed, but it can run out. Think about it that way.
Great. Thanks, Michael. And thank you, everybody who joined us today. We were really excited to have quite so many questions. I think we had over 60 in our Q&A. Just a reminder that you can definitely find written answers to anybody who didn't get theirs answered live. I know Michael did a fantastic job trying to take all of them that he could. One other quick reminder is the rest of our schedule for the week is up at under the Learn tab at fairbanksmuseum.org, and you'll see a virtual learning on the drop-down menu, and you can find all of our classes for this week. We'll be putting up a schedule for next week soon. We're developing a lot of new content, so we're excited to have you join us again next week if you're able. And for those of you on our YouTube, please remember to always join us on Zoom if you want to have a little more interactivity, but you're definitely welcome to join us on our YouTube live stream. And we, I guess, can offer or end with a nice welcome for everybody who might join us on Kingdom Access Television tomorrow. So thank you again for everybody for joining us, and find the video of this class if you have friends or family members who missed it. It will be on our website as well, where I mentioned in an archive section. So thank you again, everybody. We had a great class today, and we appreciate you all joining us. And of course, thank you to Michael for all of your excellent answers to questions and your explanations of energy and energy antics today.
Thank you guys for your really excellent questions. It's very good to still, it's great to be in class in person and be able to answer questions. And I was afraid that it would be much harder for kids to ask questions, through the internet like this. But that was actually fabulous. You guys did a super job. Thank you.
Yeah. Thanks again, everyone.